Hello, class. Like for test number 2, we're not going to be able to do a thorough review for test number 3 in class. So I wanted to tape some of the highlights of the sample test for you to use, helping you in reviewing for test number 3. Remember, that's going to be on Wednesday, May the 4th, at the regular class time, and we light up the class in 2 shifts as usual to take the tests, right, based on the first letter of your last name, correct? Just like we did for the first 2 tests. So I'm not going to go through all the problems on the sample test because that would take a long time, but I want to just hit some of the key problems. But just because I do not review a problem here on this tape, that doesn't mean that there would be a similar problem on the test itself. So be sure when you're studying, you go through the entire sample test to familiarize yourselves with the sorts of questions that might be asked on test number 3. So remember, the solutions to sample test number 3 are posted. So I'm just going to refer to that solution sheet. Sometimes I'm going to add a little bit of extra writing here, but the full solutions are posted on the Blackboard page. All right, so to start here, let's look at problem 1b. This is a pretty typical problem asking you about features of a sinusoidal curve. Remember, a sinusoidal curve is a transformation of one of our normal trigonometric functions, right? In this case, we have a transformation of the sine function. So, and we want to write down what the amplitude is, the period, and the phase shift, right? That's fairly easy to do, to write down those values if you have the sinusoidal function written in the proper form. Then you can just read these values off of the formula for the sinusoidal curve. But that proper form is what I've shown for sine and cosine, is what I have written here, right? You could use sine here instead of cosine, but I put cosine because that's what we're using in this problem. So remember, you have to have your formula written in this format to be able to read off those values, right? So you have to have this coefficient times the cosine, right? And then times the second coefficient times, and then x minus some constant. It's got to be of the form x minus a constant, right? And notice that in parentheses, the coefficient of the x has to be 1, right? So if you look at this sinusoidal curve, this is almost in the correct form. We can see the constant in front of the trigonometric function, right? In front of the cosine is -6, and so the a value here is -6. And if you take the absolute value of that coefficient in front, that a value, that gives you the amplitude. So our amplitude is going to be not -6, but the absolute value of -6, which is +6. Amplitudes or trigonometric functions are always going to be positive numbers. So take the absolute value of -6, that gives us 6. All right, so that's easy to read. Now, what's a little bit tricky here, though, is inside the parentheses, we have 2x plus pi. And remember, I said you need to have the coefficient on the x inside the parentheses to be 1. So what that means is I'm going to have to factor out this 2 from these parentheses. So that's what I did here. I factored out a 2. So when you factor out 2 from x, of course, you get left with x. But then when you factor out 2 from pi, that leaves you with pi over 2, right? So you notice 2 times pi over 2 is equal to pi. So in this form now is where you can figure out what the period is and what the phase shift is. So remember, for the period, you're going to take the k value and divide it into 2 pi, right? The formula for the period is right, is 2 pi divided by k. Well, the k in this case is 2 then, right? Okay, so if we take 2 pi and divide it by 2, we get pi. So the period for this function is pi. And now what about the phase shift? Well, the phase shift is going to be the b value, but remember we have to have this quantity inside the parentheses written as a subtraction, x minus b. Here I have x plus pi over 2. So in the usual fashion, right, I need to rewrite that as x minus a negative pi over 2. And then we can see that the b value is actually minus pi over 2, not positive pi over 2. So our phase shift is minus pi over 2. And then, of course, we can just use our knowledge of transformations, right, to understand what the graph of this, to understand better at least what the graph of this sinusoidal curve is going to like, right? Because now we know the phase shift, so we know how it's shifted left to right, we know the period, right? And then we also know the amplitude. So we know sort of what the vertical stretch, right, of the curve is going to be. So I'm not going to make a graph here, but that's the advantage of knowing the amplitude of the period and the phase shift, right? Is makes it easier to understand the graph of the curve, which can be complicated, right? That would be hard to graph by hand if you didn't have this prior knowledge of what the curve is supposed to look like. Now, speaking of graphs of sinusoidal curves, let's look at one of those. So I'm looking at next here at 2a. All right, so see, we just did one, right? So let's circle that, and now we're going to look at 2a. So here we're actually given a graph. So we're not given the formula, but we're asked sort of the same question as we were in 1b, right? We're given the graph, and we want to know, again, these key features of this. This is a sinusoidal curve. Actually, it's a transformation of the sine function. So we want to know the key features of this sinusoidal curve. What's its amplitude? What's its period? We are given that the phase shift is 0. So there's not going to be any left or right shift of this sine curve. So you know the sine curves at 0, sine is 0, right? So the sine curve at 0 starts at 0, and you know, then it goes up and comes down and comes back up again, correct, until it completes one period. And so that's what we can see here, right? This sine curve is going up, coming down, coming back up until it completes one period. That's because there's no phase shift here, right? The phase shift is 0. So the curve is not shifted left or right, but it does have a different amplitude than the normal sine curve does, right? Normally the sine curve goes up to 1 and then goes down to -1. So the normal sine curve has an amplitude of 1, but this goes up to 3. You squint, you can see that's a 3 there on the y-axis. So this goes up to 3, and the curve comes down to -3. So we can see the amplitude is 3 instead of 1. So so there's one transformation of this that this function has, right? Its amplitude is 3 instead of 1. So it has a vertical stretch of 3. What about the period now? So remember, that is how long it takes for the curve to complete one cycle, right? One full oscillation. So we can measure that by sort of looking at where the curve starts here at the origin. It starts at 0, like a sine curve, right, should. And then, of course, it goes up, and then it comes back down, and then it comes back to 0. So it completes one full cycle, right? One full period, the up, down, and up again. In what length there on the x-axis? Well, you really have to squint to see this because the graph is very small. But that on the x-axis is labeled as pi. So this sinusoidal curve completes one period in pi units on the x-axis, and then it completes another period in 2 pi units, right? And then another period, it would come back to the x-axis here at 3 pi. So the period here is pi, right? So that's kind of hard to see just because the graph is so small, but it completes one cycle, one full period in pi units on the x-axis. Okay, let's scroll down here now and look at our next problem here, which is going to be 3, and we're going to look at B, C, and D. So circle those. So these are questions, pretty straightforward questions about trigonometric inverses, right? And here we're just asked to evaluate some inverse trig functions. Let me do the last two first because those are the easiest ones. So let's look at 3D where we're asked to compute sine inverse of 20, right? Remember, what you're being asked for here is what sine inverse is computing, right? Is an angle whose sine is 20, right? When you write sine, when we write sine inverse, so sine to the -1 of some quantity equals y, we write that. What we mean is that the sine of y is equal to x. So in this case, what we are indicating is if we call sine inverse of 20y, what we're indicating is the sine of y is equal to 20. So see, we're looking for an angle y here whose sine is 20. That's what this expression means, right? But there is no angle whose sine is 20, right? Because remember, the amplitude of the sine function is 1, right? The sine function only goes up to 1 on the y-axis and down to -1 on the y-axis, right? So its range is between -1 and 1, and that does not include 20. There is no angle whose sine is 20, right? So this is actually undefined. No answer to this question. So this is kind of a trick question. You could try to compute this with your calculator and you would get the same result. If you try computing sine inverse of 20 with your calculator, you will get an error. All right. So that just means that you can't compute the sine inverse of 20. There is no angle whose sine is 20. Let's look at this. See now, working backwards here, we want the tangent inverse of 20, right? Also called arctangent, remember? So we could have also written the arctangent of 20. So you know, these all these trig functions work. All these inverse trig functions work similarly, right? If we say that arctangent of 20 is equal to y, what we mean is we're looking for an angle whose tangent is 20, right? So I want an angle whose tangent is 20. Well, okay, I don't know off the top of my head, right? I don't know an angle whose tangent is 20. This y here is not going to be one of our special angles because none of our special angles have tangents of 20. So we're really going to have to rely on the calculator to help us with this problem, right? So you're just going to use your calculator to compute arctangent or inverse tangent of 20, right? So just punch 20 in the calculator and then hit the inverse tangent key, right? That's usually the shift of the tangent key on your scientific calculator. And you'll get the result, which turns out to be approximately 1.52 in radians. So try to give your answer in radians, right? That's what the instructions say. So make sure your calculator is in radian mode. So apparently the tangent of 1.52 radians, if you compute that with your calculator, it's going to be approximately, probably not exactly, but approximately 20. So this is an estimate to 1.52 is an estimate to 2 decimal places. All right, now let's look at the last one. This is the one we can do by inspection or without using the calculator. So actually, it's a little bit harder because we're not going to rely on the calculator to compute the arc cosine or the inverse cosine of -1/2. But again, remember, what are we looking for here? We're looking for an angle. So let me temporarily call that y. And what do we know about y? That angle y, its cosine is -1/2. So we have to find an angle whose cosine is -1/2. So that's going to be a special angle, right? Because we certainly know there are angles whose cosine will be exactly -1/2. Let's see if we can find this one. So let me draw a set of axes here just to experiment a little bit. So cosine of our angle y has got to be -1/2. So we know that angle has something to do with the angle in the first quadrant, right? Whose cosine is a positive 1/2, and that is pi over 3, right? Because if you take the cosine of pi over 3, you get positive 1/2. So we know we're going to be looking for an angle whose reference angle, right, is pi over 3. Pi over 3 is not the answer because the cosine of pi over 3 is positive 1/2, not negative 1/2. But we know we're looking for an angle whose reference angle is pi over 3. But we want an angle in the correct quadrant so that the cosine will turn out to be negative 1/2. Well, where is cosine negative? It's going to be negative in the second quadrant and in the third quadrant, right? So what angle in the second quadrant would have cosine minus 1/2? Well, draw that angle in the second quadrant. Remember, we want its reference angle to be pi over 3. So we are looking at this angle, right, whose reference angle is pi over 3. What angle is that then? So what angle have I drawn here? Its reference angle is pi in the second quadrant. Whose reference angle is pi over 3. It's this big angle, right, that goes into the second quadrant. Whose reference angle is pi over 3. And so that must be 2 pi over 3, right? So I'm thinking 2 pi over 3 is the answer here. And cosine of 2 pi over 3 is indeed, we know it's negative because we're in the second quadrant. The reference angle is pi over 3. The cosine of pi over 3 is 1/2. So we know our cosine is of 2 pi over 3 is minus 1/2. So that's our answer, 2 pi over 3. Now we want to be careful because there are other angles, right? There are other angles who will give you cosine of minus 1/2. How do we know 2 pi over 3 is the one we want to settle on? Well, remember the range of the inverse cosine function, right? Range of the inverse cosine function is only going to be angles between 0 and pi. So when you apply inverse cosine to a number, always get an angle between 0 and pi. Well, 2 pi over 3 is between 0 and pi. So we know that that's the angle that we're seeking. See, we also know down here in the third quadrant, right? At 4 pi over 3, can't really squeeze this in. Let me see if I can. This angle in the third quadrant, this is 4 pi over 3. And if you compute the cosine of 4 pi over 3, you're also going to get minus 1/2 because the reference angle is pi over 3. And in the third quadrant, cosine is negative, right? But 4 pi over 3 is not the answer we want here because we need an angle between 0 and pi. So 2 pi over 3 is the right answer, not 4 pi over 3. Okay. Now let's try from problem 4. Let's look at this problem. Ooh, this looks hard. All right, so I want to look at problem 4b. Okay, so here we're just solving a triangle. So we've done that a lot in the course. And so this should be fairly straightforward, except on the previous test, right, on test number 2, when we were solving triangles, we were looking for lengths of sides. So we were given some information about the triangle, right? And they were looking for one of the sides in the triangle. But here, we're given information about the triangle, and we're not looking for the length of one of the sides. I guess that would be the length of this side, right? But instead, we're looking for the size of this angle picture, this angle theta. So we can easily use theta to set up a trigonometric equation because we know in the picture that the opposite side from theta is 8. And of course, the hypotenuse of this right triangle is 10. So you can easily write down this trigonometric equation, right? That the sine of theta is 8/10, right? Opposite divided by hypotenuse, 8/10, which reduces to 4/5. And now you can try to solve this trigonometric equation for theta, right? So how do you do that? So you've got sine of theta. Let's rewrite this. So you have sine of theta is equal to 4/5. How do I solve for theta? How do I get theta out from the sine function, right? So I just have theta without the sine is equal to some quantity, correct? And the answer is, of course, the inverse trig function, sine inverse. This is why inverse trig functions were invented, right? To help us solve equations like this one. They have other applications as well, inverse trig functions, but the primary application, the reason they were developed, is to help us solve equations like this one. So, since sine inverse and sine are inverses of one another, right, or pretty close to inverses of one another, right, they should cancel each other. So sine inverse of sine of theta should be just theta, and now we just have to compute what the sine inverse of fit says. And that you would do using a calculator, right? Because I don't know the angle sine is 4/5. That's not a special angle, but my calculator does, right? And so when we use the calculator to compute sine inverse of 4/5, in radians, we get about 0.93. So our radian answer here is 0.93. 0.93, that angle is in the proper range. Remember, when you apply the sine inverse function, you must get an angle between minus pi/2 and pi/2, right? Remember that. The range for the inverse cosine is 0 to pi, as we saw in the previous problem, but the range for the inverse sine function is minus pi/2 to pi/2, but 0.93 is between minus pi/2 and pi/2. Actually, it's between 0 and pi/2. This is an acute angle, so it's between 0 and pi/2, between 0 and 90 degrees, because it's part of a right triangle. So we know this is the correct 0.93 must be the correct answer. So see, now we can solve triangles in lots of different ways, right? We can solve for lengths of sides, but we can also now solve for angles in the triangle. I think we're going to do that again coming up here using the law of cosines, which is also going to be on this test. Now, what's a little bit trickier, right, and you're not going to like as much, are solving these trigonometric equations, kind of like solving this one, right, except a little bit more complicated version of these trigonometric equations. So I want to look at a few of those because that might be one of the harder things on the test. I'm going to pause here just for a second, the tape, but I'll be back immediately. So let's look at 5A first. When you're solving a trigonometric equation that involves sine and cosine, you're going to use an inverse trig function, so either inverse sine or the inverse cosine. But remember, the tricky part of this is we want to write down all possible solutions to the equation. And it turns out that there are infinitely many solutions, and they sort of have two basic formats. And that's really kind of the tricky part of solving these inverse trig functions, is remembering that you get lots of solutions if you try to write down all possible solutions. Now, initially, though, solving the equation is pretty straightforward. First, let's get rid of this coefficient 2 that's on the sine of x by dividing both sides by 2. This is what's shown over here on the solution sheet. So just divide by 2 and you get sine of x is equal to 1/2, which seems like a very straightforward equation, right? We know sine of x is equal to 1/2. We certainly know angles whose sine is 1/2. So it looks like this is initially just going to be a pretty easy equation to solve, right? technically, the way you do that is you apply sine inverse to both sides of this equation, and the sine inverse and the sine will cancel on the left-hand side, right? And so you just get x, and then on the right-hand side, you'll get sine inverse of 1/2. So you just have to think about what angle, right, gives sine of 1/2. That's pretty obvious, right? Because this is a special angle, and we know that pi over 6, right, its sine is 1/2. So we know that sine inverse of 1/2 is pi over 6. Okay. Remember, when you apply sine inverse to a quantity, you're going to get an angle between minus pi over 2 and pi over 2. Pi over 6 is certainly in that range, correct? So we know that sine inverse of 1/2 is pi over 6. So I've drawn that in the picture. So one of our solutions to this equation, is pi over 6. That's called one of the basic solutions to the equation. It's just pi over 6. But remember, you can generate new solutions to the equation just by adding on multiples of 2 pi to the pi over 6. That's because the sine function is periodic, right? It repeats every 2 pi units. So you're going to get additional solutions to this equation every 2 pi units away from pi over 6. That could either be in the positive direction or the negative direction. So the way I write down a full list of solutions here would be pi over 6, and then add on any multiple of 2 pi. So that would be 2 pi times k, where k can be 1, 2, 3, etc. Actually 0, 1, 2, 3, etc. Or subtract off any multiple of 2 pi from pi over 6. So again, k times 2 pi, where k is 0, 1, 2, 3, etc. All of those numbers, there are infinitely many of them, right? Because you have infinitely many choices for k here. All of those numbers are going to give us solutions to the equation. All right, so that seems like plenty of solutions already, right? We've already got infinitely many solutions, but believe it or not, that's not all of them. All right, so when you're solving these trig equations involving sine or cosine, you have to look for what's called the second basic solution. So this is the first basic solution. The second basic solution would be you've got to find another value from 0 to 2 pi, find another angle from 0 to 2 pi, right, whose sine is 1/2. Okay, so I'm looking for a second angle from 0 to 2 pi whose sine is going to be 1/2. Well, look, if the sine is 1/2, you know this angle must have reference angle pi over 6, right? Because that's how you're going to get a sine of 1/2. The reference angle must be pi over 6. 1/2 is positive, so that means this angle has to be in the first or the second quadrants, because that's where sine is positive. All right, so we've already found the angle in the first quadrant, right? Pi over 6, whose sine is 1/2. So we're restricted to the second quadrant now, right? So just draw it. I just drew a picture of it. Here's the angle, right? Its reference angle has to be pi over 6. So this angle, right, between the terminal side and the x-axis has to be pi over 6. So this has to be pi over 6, which means the angle itself would be what's left here, right? From 0 to this terminal side. And that's got to be 5 pi over 6, right? Because the 5 pi over 6 and the pi over 6 have to add up to a full pi. So that's it. There's our second basic solution. The sine of 5 pi over 6 is also positive 1/2. And so there's our second basic solution. And then again, we just add on or subtract off multiples of 2 pi, again, because the sine function is periodic. It repeats with a period of 2 pi. So all of these infinitely many numbers, all of them solutions to this equation. All right, let's try another one then. Let's get down here. I can scroll. Thought I could scroll. Oh yeah, there we go. All right, so let's skip down to, not that far, skip down to this one, D. Now, this only involves, this equation involves tangent. And tangent behaves a little bit differently because tangent has a period of pi, not 2 pi. So when you find a basic solution to this equation, one solution to this equation, you only need to add on multiples of pi, not 2 pi, because the tangent function repeats every pi units. All right, now let's see if we can find one basic solution though. So I'm going to take this equation, the tan x plus 2 equals 1, and let's solve it for tangent of x. So you do that by subtracting 2 from both sides, right? Which I've shown on this line. So we get that tangent of x is equal to, and if I fill that in, we get tangent of x is equal to minus 1, right? So we're looking for an angle, right, whose tangent is minus 1. And so that means that x, our angle, right, is going to be the inverse tangent of minus 1. So we're looking for an angle whose inverse tangent, we're looking for an angle whose tangent is minus 1. Well, we know that angle is going to have something to do with pi over 4, right? Because the tangent of, here's pi over 4. So we know our angle has something to do with pi over 4, because the tangent of pi over 4 is positive 1, right? So this angle has to be, that we're looking for, this angle x that we're looking for, right, has to be related to pi over 4. Well, in fact, its relation is it must have reference angle pi over 4. But pi over 4 is not the answer here, right? Because the tangent of pi over 4 is positive 1, not negative 1. So we have to find an angle in the proper quadrant, right, whose tangent is, whose reference angle is pi over 4, but where the tangent is going to be negative. Remember, tangent is negative. Oh, did I do this one right? Where is tangent negative? Tangent is negative in the second quadrant, right? Oh, and in the fourth quadrant. Oh, so maybe I did this right. Okay. Tangent is negative in the second quadrant and the fourth quadrant, right? But positive in the first quadrant and the third quadrant, correct? So eliminate these two quadrants as possibilities, right? We're either in the second quadrant or the fourth quadrant. Well, where could we possibly be in the second quadrant? Well, we would want an angle whose reference angle is pi over 4. So we want an angle whose reference angle is pi over 4. So in the second quadrant, that's this angle, which happens to be what? If I draw the full angle, that's going to be almost pi, but we're missing pi over 4 from that, right? So that looks like 3 pi over. So it is true that the tangent of 3 pi over 4 is negative 1. That is correct, but that's not the answer here, because again, we have to think about the range of the arctangent function. The range of the arctangent function is the same as the range of the arc sine function, the inverse sine function. And that is between minus pi over 2 and positive pi over 2. When you apply the inverse tangent function, you always get an angle between minus pi over 2 and positive pi over 2. And 3 pi over 4 is too big, so 3 pi over 4 is not going to be the answer. Likewise, if you open this angle up even further to this angle in the fourth quadrant, so if you draw an angle all the way around here to the fourth quadrant, has reference angle pi over 4, that is 7 pi over 4. This big angle here is 7 pi over 4. So it is true that the tangent of 7 pi over 4, that is negative 1. But again, that angle is too big. That is not going to be the answer to this inverse tangent equation, right? That's not going to be the solution to this inverse tangent equation, because you must get a solution between minus pi over 2 and pi over 2. So the only way to get into the fourth quadrant without going in the positive direction, which is going to make an angle too big, is to go in the negative direction. So the correct answer here is really minus pi over 4. See, if you go in the negative direction, pi over 4 units. In other words, if you draw the angle minus pi over 4, you get this angle in the fourth quadrant. Its reference angle is indeed positive pi over 4, right? So you know that the tangent of minus pi over 4, right, is going to be the same as the tangent of pi over 4, except the sign will be negative. And that would give you negative. So the correct value here for x is minus pi over. Not 3 pi over 4, not 7 pi over 4, but instead it's minus pi over 4, because you have to get an angle here. When you apply inverse tangent function, you have to get an angle between minus pi over 2 and positive pi over 2, and minus pi over 4 is in that correct range. Now you're really done, right? You just take the minus pi over 4 and then you add on multiples of pi, not multiples of 2 pi, just multiples of pi, because the period of the tangent function is pi. All right, let's try one more like this one. These are pretty tough, right? Let's try one more like this one. Looks deceivingly easy, right? Okay, we want cosine of x is 0.75. All right, so an angle whose cosine is 0.75. All right, so just by the inverse cosine to both sides, all right, to get started here. So inverse cosine of x, that's going to give you x, and then inverse cosine of 0.75. And this is not going to be a special angle, so you're going to end up using the calculator here. I have used the calculator in radian mode, so I got 0.72 on the calculator. So there is one of my basic solutions to my equation, right? 0.72, which happens to be in the first quadrant. Here's a picture of there of 0.72. So you just take the 0.72, add on or subtract off multiples of 2 pi, right? And that gives you one list of solutions to the equation. That seems all very easy. Okay. The only problem is, since this is cosine, like sine, we have to find a second basic solution. You don't have to do that for tangent, but for sine or cosine, you have to find a second basic solution, and then you have to again add or subtract multiples of 2 pi. So where is the second basic solution? We need an angle between 0 and 2 pi whose cosine is 0.75, or in other words, another angle from 0 to 2 pi whose reference angle is 0.72. So where would that be at? Well, look, where is cosine positive? It's positive in the first quadrant. It's positive in the fourth quadrant. We've already used up the first quadrant angle. That's 0.72. So I need to look into the fourth quadrant, right? Okay. So here's an angle. I've drawn a picture of it. Here's an angle in the fourth quadrant whose reference angle is 0.72. It's kind of just a mirror image of this picture, right? Of this angle in the first quadrant. Want that mirror image angle in the fourth quadrant. So there's an angle whose reference angle is 0.72. What angle is that? Right? Okay. Well, draw all the way around. Okay. So draw this angle all the way around here to the same terminal side. What would this angle, big angle, be? Well, if you went completely one circle, right, that would be 2 pi. But we didn't quite make it one circle, right, because we stopped 0.72 short of a complete revolution, right? Because we wanted our reference angle 0.72. So what we have here for this angle is 2 pi minus this piece 0.72. 2 pi minus 0.72, and that comes out to be approximately, if you do this with your calculator, 5.56. So there is our second basic solution, 5.6. And then again, we add or subtract multiples of 2 pi from that. So remember your second basic solution here, because this equation involves cosine. So that happens with sine and cosine. With tangent, though, when you're solving equations involving tangent, remember you just need one basic solution, and then you just add or subtract multiples of 1 pi. Okay, let's try now. I'm going to apply this again, our inverse trig functions again, to solve this problem. And this is again a solving a triangle. So we're going to find out some information about this particular triangle, which is not a right triangle, but now we have enough knowledge to solve also triangles that are not right triangles. So what are we trying to do here? We've shown a picture of this triangle. We're told the lengths of the sides of the triangle. One is 8. Second one is 8. This one up here up top is 13. And we want to find the size of this angle. So very similar to the problem that we solved earlier involving size and finding the size of an angle, but this is not a right triangle. But we can still now find the size of this angle using what's known as the law of cosines. So there's the law of cosines applied for this particular situation. So the law of cosine says, if you're thinking about this a particular angle in a triangle, which does not have to be a right triangle, right? The law of cosine says, well, if you take the length of the side opposite that, which in this case, since we're looking for theta, the side opposite is a here. If you square a, that's equal to the sums of the squares of the other two sides. So that would be b squared plus c squared minus the product, or twice the product of those two sides, 2 times b times c times the cosine of this angle theta that you're focusing on, right? So so there's the law of cosines applied to this picture where we're looking for the size of this angle theta. The law of cosines would look slightly different if we were looking for this angle or this angle, right? But we could also write down a version of the law of cosines for this angle or this angle as well. So let's fill in the values here because we know almost everything in this equation. We know the a, we know the b, we know the c. What we don't know is cosine of theta, right? Because we don't know the size of theta yet. That's what we're trying to find, is the size of theta. So I just filled in the values for a, b, and c here and went just going through methodically all through this arithmetic, right? So you can use the calculator to do that and help you with that. And ultimately, you'll come out that the cosine of theta is minus 41 over 128, kind of a weird value here, but that's not really important because the calculator can help us with solving this equation anyway. So cosine of theta is minus 41 over 128. And so to solve this equation, just apply inverse cosine to both sides. So you get that theta is the inverse cosine of minus 41 over 128. And of course, that's not going to be a special angle, so we need our calculator to help us with this. So I just keyed this into the calculator, cosine inverse of minus 41 over 128, and we get in degree mode 108. So in degree mode 108.68. So there it is. The size of theta is approximately 108.68 in this triangle. So don't forget about law of cosines. That will be on the test for sure. This problem A, which I'm not going to go through, but you can see the solution on the answer key. That also is a law of cosines problem. Slightly different application of the law of cosines, though. Here, we're finding the length of a side, not the size of an angle. We're given the size of an angle. Side here, we were given the lengths of the sides. We were looking for the size of an angle. But we still use the law of cosines in part A, just in a little bit different way. Okay, now let's look at another application of inverse functions, right? This time solving exponential equations. Remember, we in addition to having our trig functions and their inverses, another famous pair of inverses that are useful to us, particularly in calculus, are exponential functions and their inverse functions, which remember are the logarithmic functions. So there's the natural exponential function and its inverse, the natural logarithmic function. And that pair of inverses is very useful in helping us solve certain types of equations, just like inverse trig functions are useful in helping us solve equations involving trigonometric ratios, right? Let's look at this equation now, where we're going to use the inverse of the natural exponential function, which is the natural log function. So we want to solve 3e to the 1 minus 2x minus 12 is equals 0. So remember, this is a natural exponential, that e to the minus 1 minus 2x, right? Remember, we can think of that as being a natural exponential function. Actually, it's a transformation of a natural exponential function, but still virtually the same as natural exponential function. All right, so how do we solve this equation x? So, so remember, what we're going to do is simplify the equation a little bit first. I want to rewrite it so that I just have e to a power on one side of the equation. So I don't want the 3 on the left-hand side of the equation with the e, and I don't want the minus 12 on the left-hand side of the equation with e. Okay, first I want to isolate that e to the 1 minus 2x by itself on one side of the equation. So I just added 12 to both sides. So you get 3e to the 1 minus 2x equal 12. Then divide by 3 to get rid of this coefficient of 3. You don't want that on the left-hand side either. So divide both sides by 3. That's easy enough. And it e to the 1 minus 2x equals 4. Now that's in a position where you can now apply the inverse of the natural exponential function, which is the natural log function, right? So remember, we're going to apply the natural log function to both sides of the equation. And what that does is, since these two functions are inverses of one another, right? Natural log and exponential functions are inverses of one another. That means then that they cancel. So on the left-hand side, you don't get this complicated expression, just get 1 minus 2x. On the right-hand side, what do you get? Well, you get natural log of 4, right? Because remember, you had to apply natural log to the right-hand side, a natural log to the right-hand side as well, which gives you natural log. So we have 1 minus 2x is natural log of 4. And now we can just solve this equation algebraically, right? Okay, so just solve for x, right, in the usual way. So I think I subtracted 1 from both sides and then divided both sides by 2. So ultimately, I get this result, 1 minus the natural log to 2. That's the exact answer for this equation, 1 minus natural log 2. If you want a decimal approximation, you can use your calculator to estimate natural log, right? Okay, but there's the exact answer to the question. So this is really almost the same process as solving trigonometric equations, right? We're going to use inverse functions to help us solve this equation. Actually, let's solve this 7c, which looks like it's another exponential equation, but I don't think I'm going to end up using the natural log function here. It turns out you can solve this equation just using algebra. So you really don't need to have knowledge of inverses to solve this equation, although it looks like you do, right, when you start the problem, because you have e to the x here, which is the natural exponential function, correct? But I'm going to solve this one by factoring, because on the left-hand side, you can factor out from both terms here, both an x and an e to the x, because those factors appear in both terms. So I factor out x times e to the x, and what would be left here is from this term an x, and from this term just the minus 3. So you have x times e to the x times x minus 3 is equal to 0. That is our classic form, right, for solving an equation in algebra, right? We have a product is equal to 0. That means one of the factors is 0. So x is 0, or e to the x is 0, or x minus 3 is 0. Well, x equals 0 is already solved. Solution there is 0. X minus 3 equals 0 is easy to solve. We know x equals 3. This equation, e to the x equals 0, has no solutions, because you cannot raise a number. E is just a number, approximately 2.718. You cannot raise a real number other than 0 to any power to get 0. Okay, no number other than 0 to a power ever gives you 0. So, so this equation has no solutions, in other words, right? So we can just sort of ignore that one. There are only two solutions: x equals 0 and x equals So this one we can solve by factoring. We really don't need to know the natural exponential function to solve that equation. Let's look at one more, but now here, let's look at an equation that involves logarithms, not natural exponential functions, but the principle is really the same, right? If you're solving an equation that involves the natural logarithmic function, you ultimately are going to use the inverse of the natural log function, which is the natural exponential function, correct? So same idea, we're still using inverse functions to help us solve this equation. All right, let's see what we can do to solve this equation. We're going to simplify a little bit first. Remember, when you have the sum of two natural logs, that's the same as natural log of the product. So natural log of x minus 1 times natural log of x plus 1, that's the same as natural log of x minus 1 times x plus 1. Still have 0 on the right-hand side. Now we want to eliminate this natural log, right? So we apply its inverse. So we raise e to both sides of the equation. See, the natural exponential function is what we apply here to undo, so to speak, the natural log function, or to invert more correctly the natural log function. So raise e to both sides of the equation. These two cancel each other because they are inverse functions. So on the left-hand side, you just get x minus 1 times x plus 1. That's all. And e to the 0th power is exactly 1. Any number other than 0 to the 0th power is 1. So we get x minus 1 times x plus 1 equal 1. This is just an algebraic equation. So I'm going to multiply out the x minus 1 times the x plus 1. That gives me x squared minus 1 is 1. Add 1 to both sides of the equation. So I get x squared equals 2. And then just take the square root of both sides, right? So there are your two solutions to the equation. X is either positive square root of 2 or minus square root of 2. Cool, huh? Right? Okay. So we were able to solve that equation. Now, however, as I cautioned you in class, so this is one thing you have to be careful of. When you're solving equations involving the natural log function, be sure you sort of check your solutions, because the domain of the natural log function is not all real numbers. The domain of the natural log function is only positive real numbers, not even including 0, only positive real numbers. So notice that when you take minus square root of 2, it's okay for positive square root of 2, but when you take minus square root of 2 and try to check that answer by plugging it back into this equation, you will get minus square root of 2 minus 1. That is a negative number, and you cannot take natural log of negative numbers. You can only take natural log of positive numbers, not even 0. So, so minus 2 is what's called an extraneous solution. We arrived at it legitimately. I mean, our solution steps are okay. It's just that's not a valid solution to the equation. So that sometimes happens when you're solving equations involving natural log. So you do have to sort of partially check your answers to make sure you don't have an extraneous solution. The same problem doesn't happen with positive square root of 2. If you plug in positive square root of 2, you get positive square root of 2 minus 1, which is still positive. It's a small number, but it's still positive. Positive square root of 2 minus 1, still positive. And then, of course, square root of 2 plus 1 is definitely positive. So, so that that solution may check, but minus square root of 2 definitely is an extraneous solution. Okay, I'm going to pause again here for a second, and then briefly, and then we will resume. Okay, let's look at problem number 8. So now we're switching to polynomials. So we've just done this in class, so you're going to be really familiar with the solutions to these types of problems, but this will be on the test, right? So you have to make sure that you reviewed this carefully. So let's look at problem number 8. Here we're given this is definitely a polynomial function, right? Notice the terms are all just whole number powers of x. A whole number are integers that begin with 0. So that would be 0, 1, 2, 3, etc. And so you can see here we have x to the first power, x to the third power, x squared. The 6, you can think of that constant as being 6 times x to the 0th power, because x to the 0th power would be 1, right? So, but x to the 0th power is that's a whole number. 0 is a whole number. And so, so this is definitely a polynomial expression, right? Definitely a polynomial function. Its leading coefficient is -1, not 10, so don't get fooled by that. The leading coefficient is the coefficient of the highest power of x. So this coefficient is -1. The highest power of x is 3, so that's the degree of the polynomial. So the degree here is 3. The constant coefficient, that's pretty easy to find, right? That's just going to be the constant in the formula, which in this case is 6. All right, so now let's look at the key thing that we want to discover about polynomials, right? Which is their zeros, right? Or their x-intercepts. So in part D, it says use synthetic division to factor the expression x minus 3 from the formula for f of x, right? So so we can see that formula for f of x, and we want to factor out x minus 3. So that means we use synthetic division with 3. So remember, in synthetic division, you're going to write down the coefficients in descending order, right, of the powers. And so let's see, what would those coefficients be? That would be -1 first, because since that's x to the third power, then -1 second, since that's x squared, and then the 10 would come third, since that's x to the first power, and then the constant is 6. So you write down -1, -1, 10, and 6, and now you just carry out the synthetic division, right? So bring down the -1, 3 times -1 is -3, -1 plus -3 is -4, 3 times -4 is -12, 10 plus -12 is -2, 3 times -2 is -6, -6 plus 6 is 0. So we get a remainder of 0 here. That's great. So that means that x minus 3 is a factor of that original polynomial. In fact, that original polynomial, right, that we saw factors as x minus 3 times what? Well, what are these coefficients in our quotient, right? That would be -1 times x squared, -4 times x, and then a constant of -2. So, so this this expression, x minus 3 times -x squared -4x minus 2, that's the same as the original polynomial, right? Which, if I write it in descending powers of x, would be -x cubed minus x squared plus 10x plus 6. So if you multiply, you spent the time using your algebra, right, to multiply these two parentheses together, you would end up with, after you had added like terms, you would end up with -x cubed minus x squared plus 10x plus 6, right? The original polynomial formula. So see, that tells us then that 3 is a 0 of this polynomial, right? If you're trying to take this function and set it to 0 to find the x-intercepts, since you know it factors this way, right? You know that 3 is going to be one of the solutions to this equation, or in other words, 3 is one of the x-intercepts of your polynomial function. Now, what are the other x-intercepts? Well, those would be the solutions to this factor equal to 0, right? So take the -x squared minus 4x minus 2, set that to 0, try to solve that equation, and that would give you the other x-intercepts of your original polynomial function in addition to 3. Now, you might be able to solve this equation by factoring, but this is just a quadratic equation because the x is squared. So you might be able to solve this by factoring, but I don't think that one factors too easily. But even if you cannot factor, since this is only x squared, you can use the quadratic formula. So that's what I did here in solving this equation. There it is written here, right? I'm just going to use the quadratic formula. I think what I did, though, before I used the quadratic formula was I multiplied both sides by -1, multiply everything by -1, just to make all of these coefficients in the equation positive. See, if you multiply everything by a -1, you would get positive x squared plus 4x plus 2 equal -1 times 0 is still 0, right? So you still get 0 on the right-hand side. And that just gives me, that just means I don't have to work with a bunch of negative signs when I'm trying to solve this equation. But I'm going to use the quadratic formula. So that's what I did. I plugged the 1. This coefficient is 1, right? So I plugged the 1, the 4, the 2 into the quadratic formula. So don't forget the quadratic formula. Simplified here, and ultimately, took me a little bit of simplifying, but ultimately there's what you end up with. There are your other 2 x-intercepts for this original function f. This original function f. One of them is -2 plus the square root of 2. The other one's -2 minus the square root of 2. You can use your calculator to get decimal estimates for these numbers, but whatever those decimal estimates are, those are the other 2 zeros or x-intercepts or roots of the original polynomial. Notice we have 3 of them. That's exactly what we thought, right? Because our original polynomial had degree 3. So it might have as many as 3 x-intercepts. Same problem in number 9, essentially. Here we have a polynomial function, right? And we're looking for the x-intercepts. So we know where to look for the x-intercepts, right? That is the so-called rational zeros theorem, right? Remember, you can find rational x-intercepts, if there are any. That means x-intercepts that can be written as fractions. You can find those, right, by taking the factors of the constant coefficient and dividing them by the factors of the leading coefficient. Constant coefficient here is 5. The leading coefficient here is 2. So the possible factors of 5 are plus or minus 1 and plus or minus 5. Possible factors of 2 are plus or minus 1, plus or minus 2. You take all those quotients, all these factors divided by all of these factors, you get this list of possible rational roots, rational zeros, or rational x-intercepts. So you see, you might have rational x-intercepts at plus or minus 1 or plus or minus 5 or plus or minus 1/2 or plus or minus 5/2. Of course, not all of those numbers can be x-intercepts because this polynomial has degree 3. So that only means it has 3 x-intercepts. But if there are any rational number x-intercepts, they have to be in this list. All right, so what 9b tells you is it gives you a little hint. It says 1/2 should be a 0, right? So check that using synthetic division. So here we're going to use our synthetic division with 1/2. So that's what I've done here. Use synthetic division 1/2. There's the process. And you can see that when I use synthetic division with 1/2, the remainder does turn out to be 0. So that means bingo, 1/2 is a 0, right, of this original polynomial, correct? Actually, this polynomial, now we know factors as what? But from looking at this computation here, we know it factors as x minus 1/2 times, what's the quotient here? 2x squared minus 8x minus 10. Now, if we can just find the factors of 2x squared minus 8x minus 10, right? Then we are going to find the other zeros of this polynomial. So that's what I've done in part C, right? I took the 2x squared minus 8x minus 10, set it to 0, tried to solve that equation. Might be able to solve that using the quadratic formula, but in this case, we get a lucky break because this factors. We don't need the quadratic formula here. You can factor out a 2 first from all of your terms. So you get 2 times x squared minus 4x minus 5. And x squared minus 4x minus 5 factors as x minus 5 times x plus 1. Oh, so the other 2 x-intercepts after 1/2, the other 2 x-intercepts of my polynomial are 5 and minus 1. That's got to be all of them, right? Because this has degree 3. Here are 3 x-intercepts. 3 is the most you can have. So so that's nice, right? We were able to find all of those x-intercepts without using the quadratic formula. Let's see, are all these numbers in the original list? They have to be in the original list, right? So they are, right? 1/2, of course, is there. 5 is there, and -1 is there, right? Okay. In our original list of possible rational x-intercepts. All right, let's look at 2 more problems here. Let's look at number 12. This one is in reverse from problems 8 and 9. And then we'll also look at problem 13, which is not a polynomial problem. That's going to be actually an exponential function, a problem, an application. All right, so see, this is opposite from a problem. This problem 12 is opposite from problems 8 and 9, because here we're given the graph, and we're asked to write down the formula for the polynomial function that's graphed here. So if we look at the graph, we can see easily from the graph what the x-intercepts are, right? We can see the x-intercepts are, there's one there at -2, and there's another one at 2, and another one at 4. So so instead of being given the function and the formula for the function and being asked to find the x-intercepts, now here we're sort of being shown what the x-intercepts are, right? Because we're shown the graph and we can read the x-intercepts off the graph. So we're given what the x-intercepts are, and we're asked to write down the formula. So we're going in reverse here. Well, what does the formula have to look like, right? Since these, since we know that the x-intercepts here are -2, 2, and 4, we know then that in the answer to our problem, when we factor, the answer to our problem is a polynomial, right? Because we're told it's a polynomial. We know when we factor that polynomial, we're going to get these factors that correspond to these x-intercepts. So that would be x minus a -2, which is x plus 2, x minus 2, and then x minus 4. So we know our polynomial factors something like this. The only thing we don't know is there might also be a coefficient here other than 1 in the formula for this polynomial. That's what we have to take into account. So we don't exactly know that our answer is just x plus 2 times x minus 2 times x minus 4, right? It's something like that, but it may not be exactly just this product, because we may also have a coefficient here in front of that product. That's what we have to figure out. So I'm going to call that coefficient A. You can call it anything, really. I'm just going to call it A. And I got to figure out what's the right value for A, so that I know this formula matches this graph exactly. I know the x-intercepts are going to match, but how can I make sure the rest of the graph matches this formula? Well, what do I know about the rest of the graph? Not a whole lot, but I can see, oh, the y-intercept here is 4, right? So that's a really important clue. I know the y-intercept of ultimately of my function, the y-intercept has to turn out to be 4. So how do you find the y-intercept of a function? You evaluate p of 0, right? So that's what I did. I evaluated p of 0 here, but without knowing quite what the correct value for a is, right? So plug 0 into your formula. So you get this coefficient a times 0 plus 2 times 0 minus 2 times 0 minus 4, right? And if this formula is going to match this graph, that y-intercept has to turn out to be 4. So you get this very convenient equation, right? A times this product has to be equal to 4. And that equation now we can solve for A. So we can figure out what the right A value is. Well, when you multiply these parentheses together, that's 2 times -2 times -4. That's positive 16. So we have positive 16A is equal to 4 because the y-intercept has to be 4, right? Because that's what I see in the picture. Then just divide both sides by 16. So you get A is equal to 1/4. Oh, so I know the right coefficient here to put into my polynomial function formula is 1/4. That will give me the correct y-intercept. when I graph the function. So there it is. There's my formula. P of x is 1/4 times x plus 2 times x minus 2 times x minus 4. You don't have to expand that product. You don't have to multiply the x plus 2 times the x minus 4 times the x minus times the x minus 2 times the x minus 4. That's going to take a little while to do that product, right? Don't need to do that. It's not asked to simplify, right? You're not asked to simplify. Here's the formula for the polynomial graphed here in factored form. That's good enough. All right, last one that we're going to look at here is number 13. So this is really a very typical algebra problem. What's a little bit unusual about it is because it has embedded in this function, we have embedded there this natural exponential function, right? So let's see what this function tells us. Says the lake on a fish farm is stocked with initially with 500 fish, and the population is going to grow according to this curve. Wish we could see a graph of that curve. Unfortunately, I did not make a graph of that. I suspect what's going to happen is initially, and we're going to get a graph probably that looks something like this. Initially, the population is going to grow kind of rapidly, and then it's going to kind of level off, right? Because you're going to get eventually a maximum number of fish that can survive in this lake, right? Just based on the size of the lake and the amount of food that's available to the fish, right? So the population won't grow indefinitely. It may grow at first rapidly, but then eventually it will level off at some stable population, I'm thinking. All right, but we're not asking about the graph anyway, or not directly about the graph. What we want to find is when the fish population reaches 2,000. So apparently it's going to grow. It's going to start at 500 and it's going to grow. And we want to find when it grows to 2,000. So how many months does that take? The t variable t here, the input variable here is time, elapsed time in months. So we want to know how many months does that take to hit 2,000. Apparently it's 7.79 approximately, but let's see how we found that. So that's pretty easy to do, right? This is the formula that gives you the population, correct? So just take that formula and set it to 2,000 because you want the population to be 2,000, and then you're just left with an equation to solve for t. So that's the hard part of the problem, right? It's not setting it up, not understanding it. It's trying to solve that equation for t. So how do we do that efficiently? Well, let's see. I don't like this fraction here, so we can get rid of the fraction by multiplying both sides by the denominator. So I'm going to multiply both sides by the 1 plus 19e to the minus t over 5. So I multiplied both sides by that. Of course, they cancel. Those denominator, that not denominator will cancel on the right-hand side. So you'll just get the numerator, which is 10,000, and then you get this product on the left-hand side. Now, let's see. I think I divided. I pulled a trick here. I did not multiply the 2,000 into the parentheses. I immediately divided both sides of the equation by 2,000. So I just divided the left by 2,000 and the right by 2,000. And the 2,000 divides out on the left, and you just get, of course, what's in the parentheses, which is 1 plus 19e to the minus t over 5. And then on the right-hand side, 10,000 over 2,000 is 5. So I dispatched the 2,000 really quickly there out of the equation. That's nice because it makes the numbers a lot easier to work, right? Now, let's see. This is an exponential equation, right? See, I've got this natural exponential function in the equation trying to solve for t. So what do I want to do? We had an example of like this one earlier, right? You want to isolate the exponential function on one side of the equation by itself. I just want e to a power on one side of the equation by itself. So I subtracted 1 from both sides of the equation to get rid of the 1 here on the left-hand side. That left me with 19e to the minus t over 5 equals 4, and then just divide both sides by 19. So you get e to the minus t over 5 equals 4 over 19. And now we're going to apply our inverse, right, of the natural exponential function, which is the natural log function. So apply the natural log function to both sides. These cancel on the left-hand side. So you just get the exponent, which is minus t over 5 is equal to whatever the natural log of 4/19 is, right? Who knows? But the calculator knows. And before I use the calculator, though, I think I'm going to multiply both sides by 5, right? So I multiplied both sides by 5 to cancel this 5, and multiply both sides by -1 to cancel this minus sign. So in other words, I multiplied both sides by -5. When you multiply both sides by -5, you get just t on the left-hand side, and on the right-hand side, you get -5 times the natural log of 4/19. And apparently, with the calculator, that turns out to be approximately 7.79. So there's our result. Okay, well, I hope that review will help you some with the test on Wednesday, right? Wednesday, May the 4th. And continue working on the remaining problems on the review, right? Make sure you've gone completely through the review, and also be sure you finished all your homework right before the test on Wednesday.